In this video, we're going to find the area of the surface that's defined as the graph of a function of two variables over a region in the xy plane. So we're given the function z equals f of xy, and we've got some region r in the xy plane, and we're going to approach finding the area of the surface much like we've done everything else when we've found, say, volume under a surface. The first thing we're going to do is we're going to partition our our region into rectangles. The rectangles will have sides of length delta x and delta y respectively. And then as a sample point, remember when we do integration, we can use any sample point in our partition that we want. In this case, just to make the notation easier, we're going to use our sample points as being the corner of the rectangle that's closest to the origin. All right, so at this point, we can, since we're given the equation of the surface is z equals f of xy, we can find the tangent plane to that surface at that point. And what we'll do to help us approximate what the surface area is of the surface over the region, over that rectangle, over that little piece that we've partitioned into the xy plane, instead of trying to find the area of the surface over that little rectangle, we're going to find the area of the parallelogram that lies in the tangent plane. Because we know how to find areas of parallelograms with parallelograms that are defined as vectors. So we're going to use that to help us figure out an approximation of the area of the surface over that little rectangle, and then we'll add up all those little approximations, and that'll help us get a formula in terms of a double integral for the surface area. All right, so to give a little bit of a picture idea of what we're talking about, here is the point that we're interested in. So say this is our rectangle down on the xy plane. This would be the corner that's the closest to the origin. Here is the point that we're calculating the tangent plane at. We're only going over this rectangle, so we'll take this vector going this way that's directly above this edge of the rectangle, and this vector going this way that's directly above this edge of this rectangle, and look at the parallelogram that we formed. The reason why we're going to use this is because this is a pretty good approximation. The second picture is just the first picture rotated. Notice that we've got the surface over that region, but here is the parallelogram, and notice those are pretty close together. And you can imagine that we even get better approximations the more and more rectangles we have, i.e. the smaller that we make delta x and delta y, the more fine, or I should say the finer we make the partition. All right, so we can figure out how to find this parallelogram by looking at the tangent lines, okay? So going back to the picture here real quick, this line is tangent to this curve, where we just look at the x as the y coordinate is constant along that particular edge of that rectangle. We get a curve that we can figure out a tangent line to by just using the partial derivative with respect to x, because that's in the x direction. We move delta x in that direction, so the z coordinate will move the partial times delta x in the z direction. Likewise, we can find the other vector that defines that parallelogram by looking at the tangent line in the y direction, again using our partial derivative with respect to y as the slope of that line. Since I have now the equation, now that we have the equations of those vectors, or I guess I should say the form of those vectors, I can calculate the area of the parallelogram defined by those two vectors as the magnitude of the cross product. So we can use our usual way of finding cross product with determinant, and we notice that we will get a delta x, delta y in every single term that we can factor out. On the I term, we will just multiply together the delta y times the f sub x delta x. We factored out the delta x delta y, so we're just left with a negative partial with respect to x. Likewise, you'll get a negative partial with respect to y times the j, and then just a 1 times the k. And you can see that here pretty quickly when you just multiply the delta x and the delta y together. The magnitude of that, well, this is just a scalar times that vector. I can pull the scalar out in front. Technically, it's the absolute value, but delta x and delta y are positive values, so I don't need to worry about putting absolute value on that. we'll get the square root of the partial with respect to x squared plus the partial with respect to y squared plus a 1. Add all these up. Now, this will give us an approximation of the surface area over the region. It gives us a double sum of this expression. And notice that we have delta x times delta y here, so we get a double Riemann sum. We recognize this as a double Riemann sum, so if we let m and n go to infinity, this should be a comma in between the m and the n. So that's a typo. This should be m comma n go to infinity, not m times n. That's what that looks like. We're letting both m and n go to infinity, because remember, to your definition of your double integral, you do a double limit of a double Riemann sum. So m and n both have to go to infinity. In any event, this gives us our double integral formula now for the surface area. The surface area will be the double integral over the region of the square root of the sum of the partials squared plus 1. Notice this mimics our arc length formula. Remember back in one-dimensional, well, I guess I should say two-dimensional curves, we have the 1 plus the derivative squared, and then do the square root, gave us the arc length. This is the three-dimensional extension of that particular notion. All right, so let's see if we can use this formula to help us get a surface area. We want to find the area of the plane that lies inside the cylinder, x squared plus y squared equals 9. So I first need to change the equation that we have into a function of x and y, so I solve for z. Then, according to our surface area formula, it's the double integral over the region of the partial with respect to x squared, and the partial with respect to x here is -2, plus the partial with respect to y squared, partial here is -5, plus 1. We just get square root of 30, which is a constant, so we can pop that out in front of the double integral. So we get square root of 30 times the double integral of the region of just dA. Well, we recognize that as just the area of the region, R. Okay, so we're looking at the area of this plane that's inside this circle. Well, this circle, x squared plus y squared equals 9, is defining, or the cylinder, I should say, x squared plus y squared equals 9, actually is defining our region in the xy plane that we're integrating over. The intersection of that circle, or excuse me, that cylinder with the xy plane is a circle, right? And then, of course, it'd be a disk, since we're inside that cylinder. So anyway, if we want the area of the region, basically we want the area of the circle in the xy plane, which in that case, the radius here is 3, so we get 9 pi times root 30 as our surface area. Let's do another one. Let's say we have the surface z equals xy. We want the area of that lies inside the cylinder x squared plus y squared equals 1. Partial with respect to x is y, partial with respect to y is x. So the surface area here is the double integral over our region of square root of y squared plus x squared plus 1, dA. Well, I recognize that I'm integrating over a region in the xy plane that's a circle, and I also see x squared plus y squared underneath my radical. That screams to me that I should be converting this integral over to polar coordinates, because I can describe the circle as r goes from 0 to 1, theta goes from 0 to 2 pi, and I can replace the x squared plus y squared with r squared, and then remember our dA gets replaced with r dr d theta. So I get integral from 0 to 2 pi, integral from 0 to 1 of r square root of 1 plus r squared dr d theta. I can break that now. This is, there are no r's in the theta part, there are no thetas in the r part, so I can split this into in there, then I can split my integrand up into function of r times function of theta. So I can actually break this integral into two pieces, a product of two integrals, one with the r piece and one with a theta piece. Integral from 0 to 2 pi of d theta is just 2 pi. This is a square root of u idea, but I'd need a 1/2 to adjust. And then u to the 1/2, its antiderivative is 2/3 u to the 3/2. So putting all those pieces together, we get a 1/3, 1 plus r squared to the 3/2, evaluated from 0 to 1. And I can put the 1/3 with the 2 pi, get 2 pi over 3, and then when we plug in 1, we get 2 root 2. When we plug in 0, we get 1. So we get 2 pi over 3 times 2 root 2 minus 1.